Hiya! In this video, I'll talk about my research on fundamental connections between opacity and error detection in linear systems. This is a joint work with my guide, Dr. Vaipakateva. So the main question in this talk is, can a linear system be both private and secure? So the short answer to this question is no, and we will see why it is so in the next few slides. So we'll start with some foundational basics. So we'll begin with what privacy is in this setting. So let's assume we have a bank and we have a money truck that starts from the bank, which is at location 0. It also has the legend will we have the value 1 if the truck carries money. So the truck carries the money from location 0 to 5 to 12 at time instance k equals 0 to 1 to 2. Let's assume we have another truck which also goes along with the money truck, but which does not carry any money, the same dimensions and the same location. In this way, if an eavesdropper obtains the location information, then he only sees the current location of the trucks. But because there are two trucks which are at the same location at each points of time, he's not able to distinguish if the truck is carrying money or not. So in this way, the privacy of the money is made, and that is termed as opacity. So now we go on to security. So let's assume the same truck goes from 0 to 5 to 10, but with the velocities 0, 5, and 7. This truck could also have started from the same location, but with an initial velocity of 5. In that case, the location would have been 0, 7, and 12. In linear systems, generally attack detection is checked by checking if the location, the values are according to the normal and trajectory values. So in this case, 0, 5, 10, 0, 7, and 12 both go to the attack detector and say the attack detector says that there's no attack that is occurring. However, let's assume there is an attacker present in the system. And this attacker adds an additional input such that the location of the truck goes from 5 to 7. So this new location of the truck is the same as the one that was if the velocity had been initially 5. So because of this, since the attack detector only sees the location values, he is not able to detect if there is an attack occurring or not. However, if the velocity information was also fed to the attack detector, then the attack would have been detected. However, then the privacy could not have been established. So this is a fundamental trade-off. We'll analyze this theoretically. Let's assume we have a system model, which is a normal model, and we have the system matrices A, B, C, and D. The state is X, which is like the position and velocity. The observed value is Y, and the U is like the acceleration. The attack model is where the attack input is added, which is U tilde, and the B tilde and D tilde are the attack matrices. So there's a subspace for each linear system, which is called the weak dimensional subspace. It's a subspace of the initial states x naught. So for which there exists an input sequence U0, U1, U2, for which if you add these inputs to this state, the output y is always 0. So this subspace will be used to establish the trade-off between security and privacy. The fundamental trade-off is that the first lemma is if you have a system for which the system's states can be made opaque or private, the unobserved subspace will be not equal to 0. It's an if and only if condition. Similarly, undetectable attacks exist on the system if and only if the weak dimensional subspace of the attack model is not equal to 0. We go on to the fundamental theorem using this lemma. So the theorem says that if you have a system that is private, then it is always true that undetectable attacks exist. However, in the reverse case, it's not always true, but a sufficient condition is that subspace can be subset of the other. So in conclusion, the main results are the private system is always insecure, and the secure system cannot be made private. So the application areas are one is in smart grid, another is in remote automotive systems, other areas may be healthcare, etc. So thank you for the talk, for attending the talk. So